There's a spacecraft 12 billion miles from Earth that just rewrote something scientists had accepted as fact for almost 40 years. Through old data looked at correctly for the first time. That's the real story of Voyager 2's latest contribution to science. No fabricated signals needed here. Stick around because this one is genuinely remarkable. Let's start with the basics because Voyager 2's story is stranger than most people realize even before we get to the recent discovery. Voyager 2 launched on August 20th, 1977. Its mission sounded ambitious at the time but almost modest compared to what it eventually became. Visit Jupiter, visit Saturn. If everything went perfectly, maybe continue on to Uranus and Neptune. Send back data, then fade into history. That was the plan. Instead, Voyager 2 kept going, past every planet on its list, then past the edge of the solar system itself, and it's still transmitting data today, nearly 50 years after launch. It remains the only spacecraft in human history to fly past all 4 outer planets: Jupiter, Saturn, Uranus, and Neptune. No other mission has repeated that, and none is currently planned to. On November 5, 2018, after more than 41 years of flight, Voyager 2 crossed the Heliopause, the boundary where the sun's constant outward stream of charged particles, called the solar wind, finally gives way to the material that fills the space between stars. It became only the second human-made object ever to cross that threshold, following its twin, Voyager 1, 6 years earlier. But Voyager 2 had something its twin didn't have anymore by that point, a fully functioning plasma science instrument, capable of directly measuring the density, temperature, and flow of charged particles around the spacecraft. That single working instrument mattered enormously. Before the crossing, it recorded plasma from the solar wind flowing steadily around Voyager 2. Then, at a specific moment, that flow simply stopped. The solar wind had ended. Voyager 2 had physically measured directly the exact place where the sun's influence gives way to the galaxies. That was a genuinely historic result, one of the clearest direct confirmations ever recorded of where our solar system's protective bubble actually ends. And what Voyager 2 found on the other side of that boundary wasn't the calm, simple, mostly empty region scientists had expected. Instead, it found a boundary that behaved less like a clean wall and more like an active, leaking membrane with particles from inside the heliosphere still escaping outward, and particles from interstellar space pushing inward at the same time. That discovery alone would be enough to make Voyager 2 one of the most scientifically valuable spacecraft ever built. But its biggest recent contribution to science didn't come from the edge of the solar system at all. It came from a flyby that happened back in 1986. On January 24, 1986, Voyager 2 became the first, and to this day the only spacecraft to fly past Uranus. That single encounter became the foundation for nearly everything scientists thought they knew about the planet up close. Its magnetic field, its radiation belts, its moons. For almost 40 years afterward, Uranus was treated as the strangest, most extreme magnetosphere in the entire solar system. Its radiation belts were intensely energetic. Its surrounding plasma environment appeared almost completely empty. Its magnetic field was wildly misaligned, tilted at a strange angle relative to the planet's own rotation. Scientists built decades of theory around those observations. Maybe Uranus's large icy moons, which normally would be expected to feed particles into a planet's surrounding magnetic environment, were simply inactive. Maybe the entire planet just behaved unusually, permanently, as a fundamental feature of what Uranus actually is. That was the accepted picture, until researchers went back and looked at the data again. In November 2024, a team led by Jamie Jasinski, a space plasma physicist at NASA's Jet Propulsion Laboratory, published a study in the journal Nature Astronomy that fundamentally re-examined the Voyager 2 Uranus flyby data. Rather than only looking at measurements taken during the flyby itself, Jasinski's team studied the solar wind conditions in the days and months surrounding it, using data Voyager 2 had also collected before and after passing the planet. What they found was striking. In the days immediately before Voyager 2's closest approach to Uranus, the solar wind, the stream of charged particles constantly flowing outward from the sun, had suddenly intensified dramatically. The dynamic pressure of that solar wind increased by a factor of roughly 20 compared to typical conditions. That surge in solar wind pressure compressed Uranus's magnetosphere significantly, squeezing and distorting the very environment Voyager 2 was about to fly through and measure. When Jasinski's team looked at 8 months of solar wind data collected around Uranus's orbit, they found that the specific conditions present during Voyager 2's flyby only occurred somewhere between 4 and 5% of the time. In other words, humanity's only close-up look at Uranus happened to occur during one of the most extreme, least typical moments possible. A rare compression event that may have completely distorted the picture scientists built of the planet for the following 4 decades. Jasinski summarized the finding directly. He said if Voyager 2 had arrived just a few days earlier, it would have observed a completely different magnetosphere at Uranus entirely. Think about what that actually means. Humanity has sent exactly one spacecraft to Uranus, ever. It flew past once, and that single encounter may have captured the planet during an unusual, temporary event rather than its normal, everyday state. The implications reach further than just correcting old data. If the extreme, mostly empty plasma environment Voyager 2 recorded was caused by that rare compression event, rather than being Uranus's normal condition, then the moons orbiting inside that magnetosphere may not be nearly as inactive as scientists had assumed for decades. Some of Uranus's large icy moons could actually be feeding particles into the surrounding magnetic environment under normal conditions, something the 1986 flyby simply couldn't have detected if it happened to catch the system in an unusually disturbed, temporarily plasma-depleted state. That opens up a genuinely exciting possibility. If those moons are more active than the old data suggested, some of them could potentially host more interesting geological or even ocean-related activity beneath their icy surfaces than the standard picture of Uranus's system ever allowed for. None of this is confirmed yet. Nobody is claiming these moons definitely have hidden oceans or active geology based on this reanalysis alone. But it opens a door that had effectively been considered closed for almost 40 years, based on a single data point that may never have represented Uranus's typical state in the first place. This finding matters beyond Uranus specifically too. It's a genuine, humbling lesson about the limits of studying any planet using a single flyby. Every one of the outer planets humanity has ever visited up close, Jupiter, Saturn, Uranus, and Neptune, has largely been studied through brief flybys rather than long-term orbital missions, with the exception of Jupiter and Saturn, which eventually received dedicated orbiter missions decades later. Uranus and Neptune have never had that luxury. Voyager 2's single pass by each remains the only close-up data humanity has ever collected. If a single rare, several-day solar wind event could distort our entire understanding of an entire planet's magnetic environment for nearly 40 years, it raises a genuinely important question about how confidently scientists can generalize from any single planetary flyby for any world humanity has only visited once. That's part of why Uranus has become a genuine priority target for future missions. The National Academy's 2023 Planetary Science and Astrobiology Decadal Survey specifically prioritized a dedicated mission to Uranus as one of NASA's next major planetary science goals, partly because of exactly this kind of open question. A single brief flyby from nearly 4 decades ago simply isn't enough to fully understand a planet this complex and this poorly studied. So where does Voyager 2 itself stand today, nearly 50 years after launch? It's currently more than 12 billion miles from Earth, moving through interstellar space at roughly 34,000 miles per hour. It runs on radioisotope thermoelectric generators, converting heat from decaying plutonium into electricity, a power source that loses a small amount of output every single year permanently, with no way to reverse it. To manage that shrinking power supply, NASA has had to make increasingly difficult choices about which instruments to keep running and which to shut down. In 2024, engineers powered down Voyager 2's plasma science instrument specifically to conserve energy, the very instrument that had provided the direct measurements confirming its 2018 Heliopause crossing. That's the genuine tension at the heart of this mission right now. The farther Voyager 2 travels and the longer it survives, the more scientifically valuable its position becomes, since nothing else currently exists anywhere near where it's traveling. But every year that passes also brings it closer to running out of the power needed to keep collecting and transmitting that data at all. Every command sent to Voyager 2 takes many hours to arrive. Every response takes just as long to come back. There's no repair mission possible, no backup spacecraft nearby, and no way to replace any component that eventually fails. And yet, against every reasonable expectation set back in 1977, it's still out there, still transmitting. Still occasionally forcing scientists to revisit decades-old assumptions, as it just did with Uranus. That's really the through line connecting Voyager 2's biggest discoveries, both old and new. It's not just that the spacecraft found something dramatic in the moment. It's that data collected by an aging machine, launched before most of the scientists currently studying it were even born, can still meaningfully reshape our understanding of the solar system decades after the original observations were made. A flyby completed in January 1986 just rewrote a chapter of planetary science in November 2024. A crossing made in November 2018 is still actively shaping how researchers think about the true structure of the boundary between our solar system and the wider galaxy. Voyager 2 isn't just a machine slowly running out of power at the edge of known space. It's an ongoing scientific resource, one whose full value researchers are still in the process of discovering, sometimes decades after the original data was even collected. Even now, Voyager 2 continues to answer questions scientists weren't even asking when it launched. Modern computing techniques allow researchers to reanalyze decades-old measurements in ways that simply weren't possible during the 1980s. Tiny details once buried inside enormous datasets can now be separated from background noise, compared with newer observations and interpreted using far more sophisticated models than the mission team originally had available. That means Voyager's scientific mission isn't limited to the data it sends home today. Every measurement stored in its archives remains a resource that future generations can revisit with fresh ideas and better tools. In a very real sense, the spacecraft keeps making discoveries twice: once when it records the data, and again years later when scientists uncover something they hadn't recognized before. The Uranus result is a perfect example of that process. Instead of revealing that earlier researchers made mistakes, it demonstrates how science naturally improves over time. The original interpretation matched the evidence available then. As more information about solar wind behavior became available, researchers gained the context needed to understand that the flyby captured an unusually compressed magnetosphere rather than an average one. That willingness to revisit old conclusions is one of science's greatest strengths. New discoveries don't always require new spacecraft. Sometimes they come from asking better questions about observations we've already collected. Voyager 2 reminds us that data never truly stops being valuable, especially when it comes from places humanity has never visited again. The renewed interest in Uranus has also strengthened the case for sending another dedicated mission there. Planetary scientists increasingly argue that the ice giants represent one of the biggest missing pieces in our understanding of how solar systems form and evolve. Thousands of exoplanets discovered around other stars appear to fall into a size range similar to Uranus and Neptune. Yet our direct knowledge of those worlds still comes largely from a single flyby, lasting only a few hours. An orbiter spending years around Uranus could repeatedly observe its atmosphere through changing seasons, monitor its unusual magnetic field over long periods, and study its moons in detail rather than during brief flybys. It could answer questions Voyager 2 simply wasn't designed or given enough time to investigate. Those moons are especially intriguing. Several scientists believe that beneath their icy crusts, some could contain subsurface oceans kept liquid by internal heat. If future missions confirm that possibility, Uranus's system could become another important location in the search for potentially habitable environments beyond Earth, alongside places like Europa and Enceladus. Voyager 2 also changed the way engineers think about designing long-duration spacecraft. Hardware originally expected to operate for only a handful of years has survived nearly half a century because of careful engineering, conservative power management, and continuous support from mission teams adapting to new challenges year after year. Engineers today still rely on lessons learned from Voyager when designing missions intended to travel far from the sun, where solar panels become impractical and spacecraft must survive for decades with almost no possibility of repair. The mission has become both a scientific laboratory and an engineering textbook. Communication itself has become an extraordinary achievement. Signals transmitted by Voyager 2 reach Earth with only a tiny fraction of their original power after traveling for more than 18 hours across interstellar space at the speed of light. By the time they reach NASA's Deep Space Network, those signals are unimaginably faint. Yet sensitive antennas and advanced processing techniques can still separate them from the background noise of the universe. It's remarkable to consider that every scientific graph researchers publish today begins as an almost unimaginably weak radio whisper crossing billions of miles of empty space before finally reaching Earth. Eventually that conversation will end. The spacecraft's radioisotope generators continue losing electrical power each year, forcing engineers to gradually shut down more instruments to keep the remaining systems operating as long as possible. At some point in the coming years, there simply won't be enough electricity left to power the transmitter. So the latest Voyager 2 discovery isn't really just about Uranus. It's about the value of preserving data, questioning long-held assumptions, and recognizing that the universe often reveals its secrets gradually rather than all at once. Sometimes the biggest breakthrough comes not from building a brand new spacecraft, but from looking at an old one with fresh eyes. And perhaps that's Voyager 2's greatest legacy. It has shown that exploration doesn't end when a mission flies past its destination. As long as curious people continue asking new questions, even measurements collected decades ago can reshape our understanding of the cosmos. For a spacecraft that was only supposed to last 4 years, that's an extraordinary achievement and one that continues to inspire scientists, engineers, and explorers around the world. If you want to keep following what Voyager 2 and its twin continue to reveal as both spacecraft push further into uncharted territory, subscribe and turn on notifications. The real story out there keeps turning out to be remarkable enough without anyone needing to invent anything extra.